In this problem, we have forced air at this temperature, at this velocity, and it's cooling electronic elements on a circuit board. One of these elements is 4 meters by 4 meters, and it's located 120 millimeters from the leading edge of the board, which is over here, where x is equal to 0. Experiments have revealed that flow over a board is disturbed by the elements, and that convection heat transfer is correlated by an expression of the form where Nusselt number of x is equal to 0.04 times the Reynolds number at each x raised to the power of 0.85 times the Prandtl number to the power of 1/3. So, in summary, we are given all of these constants here, and we're asked to find the surface temperature of the chip if it is dissipating this amount of power. So, some of the assumptions we have here is that we're at steady state, the flow over the top of the chips is incompressible, and all of the properties are going to be constant. Now, to start out, we just have that Q, or this power here, is equal to the convection. Just a little energy balance here. With this equation, we're going to be solving for the surface temperature, Ts. We know the power, we know the area, and we know the temperature of the fluid, but we have to find the convection coefficient. So to do that, we're going to be using this expression here. In table 6.2, we're given these dimensionless constants, what the values are, what the equations are for each of these, where we have the Nusselt number is equal to HL over KF, where H is what we're looking for. Reynolds number is equal to VL over nu, and the Prandtl number is equal to this expression here, but we can also find it in table A4 in the appendix. Now, solving for all of these constants, plugging all these constants in, and plugging them all into this expression here, we're going to solve for H. And so I've plugged everything in, solved for H, and we get that H is equal to about 109 watts per meter squared Kelvin. Now, from here, all we have to do is plug H back into this equation that we know all the other variables for. And that solves for a surface temperature of 42.14 Celsius. And that's question 6.1.